Jeddah Tower's construction is progressing well, and this building will be the tallest building in the world soon. However, there was a long 7-year hiatus in this building's construction. After the long 7 years, the concrete below the 63rd floor had perfectly cured and hardened. Can you tell what will happen to this building if the engineers pour the concrete directly into it and resume construction? What's going on here? After 7 years, the concrete below the 63rd floor had hardened well and become too stiff, but the new concrete is relatively flexible. With the weight addition in the upper floors, it is reducing its height. This means the bottom edge of the glass facade won't move at all, while the top edge moves down. You can imagine what would happen. This issue does not happen in normal construction. There, both the top and bottom edges will move down at the same rate. The same fate is awaiting the elevator guide rails as well. This phenomenon is known as the stiffness discontinuity. The biggest problem of stiffness discontinuity is stress concentration at the interface and eventually cracks. The project manager, Ian Norman Miller, had a great solution. He didn't use the same concrete mix for the next 10 to 15 levels. The new mix is engineered with specific additives to mimic the stiffness of the older concrete below it, gradually moving back to a more flexible mix as they go higher. Thousands of extra steel dowels were drilled and grouted into the old concrete. These act like stitches, physically sewing the new section to the old 250-meter base. Moreover, the top surface of level 63 was scabbled to expose the aggregate, and high-strength epoxy bonding agents were applied to ensure the new concrete glues to the old. The height difference between Jeddah Tower and Burj Khalifa is 172 meters, but the Jeddah Tower is almost double the weight of the Burj Khalifa. The sheer weight of this 1-kilometer-tall building is borne by these gigantic piles. As the building weight increases with construction, it's natural that the foundation will settle into the soil. Engineers are okay with settlement. What they fear is differential settlement. What they found in this project was that the center of the building would settle 120 millimeters more than the other portions. That's a huge differential settlement. The result?
Can you find a solution here? To reduce the differential settlement, we have to increase the surface area of these piles. I have two solutions here: increasing diameter or increasing length of the piles. Both of them have a higher area. Which one would you choose?
If you choose the larger diameter solution, a disaster is waiting. The center would sink even deeper. The lengthier pile is the right solution. This would save the Jeddah Tower. What's going on here?
The issue is mass. Both the cylinders have the same surface area, but the one with larger diameter is twice as heavy.
This higher weight at the center will cause even higher differential settlement.
This is why Thornton Tomasetti, the structural design company behind the Jeddah Tower, selected the higher length option. The engineers are clever. Along with the increase in the length, they decreased the diameter of these piles slightly, which resulted in an increase in surface area, but maintaining almost the same weight. They decreased the length of the piles gradually towards the outer region. This pile raft foundation is the backbone of Jeddah Tower. The entire structure is built around this foundation. The shape of Jeddah Tower is unlike any other structure. If you think it's a simple triangular pyramid, no, you're wrong. Adrian Smith, the architect of the sky, was the mind behind this building's iconic shape. Welcome to his visionary design approach. Observe the morphing from the simple triangular pyramid to the final Jeddah Tower form. The secret here is that the three wings feature slightly different angles. While each individual wing maintains a uniform slope, the slight variations between them mean they meet at the top at different levels. Watch this animation, which exaggerates the angles, as the basic pyramid transforms into the striking Jeddah Tower. a clean 3D form that is both elegant and unique. From the engineering perspective, the advantage is that the asymmetrical protrusions break vortex shedding patterns. Adrian Smith used the similar buttered core system as that of the Burj Khalifa in Jeddah Tower as well. This is a Y-shaped buttressed core, a hexagonal central spine supported by 3 reinforcing wings. This tripod design provides immense lateral stiffness against high-altitude winds. As the tower rises, these wings taper, confusing wind vortexes to minimize sway. This design has one great advantage. These structural columns, in fact, act as the walls, thus reducing the wastage of useful floor area.
Here is an intriguing question for you. Can you find out a huge advantage Burj Khalifa has over Jeddah Tower? Yes, it is the usable floor area. Burj Khalifa's gross floor area is 3.3 million square feet. For Jeddah Tower, it is 2.6 million square feet.
To push a building to 1,000 meters, the physics of resisting high-altitude wind forces requires a colossal central core. The central triangular core is incredibly thick and wide. The central structure is so massive that the useful area got reduced to a relatively thin ribbon of space. Remember, Burj Khalifa's pile foundation is just 50 meters deep. We know the Jeddah Tower is almost double the weight of the Burj Khalifa. The huge weight of the building also means the concrete at the bottom region of this tower has to bear an extremely high pressure, a pressure of around 115 megapascals. Remember, normal concrete can bear pressure of just 28 megapascals. If the engineers had used normal concrete mixture in this region, you can imagine what would happen. The buttressed core is obviously the spine of Jeddah Tower. The stress analysis revealed one vital fact to the engineers. If this spine has to work perfectly, the coupling beams between the central core and wings should be extremely strong. They are under severe shear stress due to the building's tendency to sway. The engineers had to choose the holy grail of concrete here, the UHPC. UHPC can withstand pressure more than even 150 megapascals. UHPC uses only fine sand and powders like silica fume to create a dense, uniform matrix. Moreover, it is packed with thousands of tiny, high-strength steel or organic fibers, usually 13 millimeters long. These act like a microscopic skeleton, sewing the concrete together. What is surprising is that the UHPC has self-healing capability. If a microscopic crack forms, unreacted cement particles inside the dense matrix react with moisture in the air to grow new crystals, clogging the crack before it can spread. But the cost of this super strong concrete is 10 to 20 times that of normal concrete. Due to this high cost factor, the majority of Jeddah Tower was not built with UHPC, but with high-strength concrete. This diagram illustrates usage of different concrete types in different levels. HRH Prince Al-Walid bin Talal Al Saud, the chairman of Kingdom Holding Company, is the father of the project. It was his vision to create a vertical city that would act as the anchor for the Jeddah economic city development. For the prince, the tower is a symbol of Saudi Arabia's economic power and modernization. Intended to do for Jeddah what the Burj Khalifa did for Dubai. His dream is slowly materialized by these 3 key persons: Robert C. Sin, the lead structural engineer, Adrian Smith, the principal design architect, and the commander on the ground, Ian Norman Miller.
You may anticipate nothing special about this concrete pumping. Just have a look at the cross-section of the pipe used for the concrete pumping and you will change your opinion. The pipe is of 20 millimeter thickness.
The reason? The pressure inside this pipe is 250 times the atmospheric pressure. You may imagine how a normal pipe will behave under such extreme pressure. The liquid concrete has to climb roughly 1,000 meters vertically. You may observe insulation jackets around the pipe. The concrete does not reach the top instantly. The pump used for the vertical transport is the most powerful in the world. Schwing SP 8800. Even after this, once the pump is on, it will take approximately 25 to 30 minutes for the concrete to reach the top, a slow transport of concrete, roughly 0.5 to 1 meter per second. The insulation jackets make sure that the early setting of the concrete does not happen due to Saudi's sun. The concrete used for this project is chilled and exclusively self-compacting. Engineers are planning for a relay method of concrete pumping to reach the final heights. The primary ground pump pushes the concrete roughly 600 meters up, or level 120. This leg takes about 12 to 15 minutes. The concrete is discharged into a specialized holding hopper at a high-level mechanical floor. A second high-pressure pump catches the fresh concrete and pushes it the final 400 meters. This leg adds another 8 to 12 minutes. Here comes an interesting question. What if the pump stops? If the pumping stops for more than an hour, the 12.5 tons of concrete inside the vertical pipe will begin to harden. To prevent this, every time a pour finishes, they use high-pressure water or air to push a sponge called a pig all the way through the 1,000-meter pipe to scrub it clean. If they didn't, concrete would stick to the walls, causing a permanent blockage. You might have seen Jeddah Tower's jump form concreting technology. Here, the form climbs like a robot. After a floor's walls are poured and reach a specific strength, hydraulic jacks jump the entire formwork system, including the worker platforms, up to the next level. The concrete is now poured into the new form cavity. We have already seen this. Inside the usable floor area of Jeddah Tower, you don't have to worry about the irritating structural columns. Concreting of this tower is progressing well, but in early 2018, construction came to a grinding halt, with the tower standing at approximately 63 floors. The end was caused by a massive political and financial shift in Saudi Arabia. The visionary behind the tower, Prince Al-Walid bin Talal, and chairman of the contractor, Saudi bin Laden Group, Bakr bin Laden, were detained in this period. The SBG faced significant financial restructuring and leadership changes during this period. Without their full capacity and the prince's immediate oversight, the site went silent. For years, the world wondered if the Jeddah Tower would become the world's tallest white elephant. Cranes sat rusted atop the structure, and the exposed steel was subjected to the corrosive, salty air of the Red Sea. Another major reason for the halt of Jeddah Tower construction was an accident related to SBG. In September 2015, a crawler crane collapsed at the Grand Mosque in Mecca, killing 111 people and injuring many. This tragedy led to a temporary ban on SBG receiving new government contracts and triggered a financial crisis for the company. The injured of this incident and the families of those deceased received compensation from the state. However, in most of the cases, if you're injured, you have to fight against the contractor or government to get your compensation. The Disney World case of 1977 is a classic example of it. At age 18, Tim Morgan, younger brother of attorney John Morgan, was paralyzed from the neck down in a catastrophic lifeguard accident at a local resort near Disney World. The incident occurred while Tim was employed at a Disney-affiliated resort in Florida. Tim didn't receive sufficient legal justice. He received a very low settlement, and the family felt the legal system was rigged against them, which profoundly impacted John Morgan. Driven by this injustice, John Morgan established his law firm, Morgan & Morgan, with the mission of representing individuals against large corporations and insurance companies. Today, Morgan & Morgan is America's largest injury law firm. Morgan & Morgan has a proven track record of fighting for the people for over 35 years. If you're injured by someone else's negligence, you can check out Morgan & Morgan, and their fee is free unless they win. For more information, you can go to forthepeople.com/Sabin found in the description below. Luckily, after a long hiatus from 2018 to 2023, the project was completely rebooted as part of Saudi Vision 2030. Construction is now in full swing. The tower has recently surpassed the 100th floor. The momentum has shifted from if it will be finished to when. The observation deck of Jeddah Tower is at a height of 600 meters. Prince Al-Walid bin Talal Al Saud wanted a single elevator ride to reach this level. Let's assume the engineers used traditional steel cables for this elevator. The weight of this cable alone would be 27 tons. Remember, the weight of the empty elevator car plus the passenger is around 7 tons only. To lift 7 tons of load, 27 tons of cable? In a traditional skyscraper, once the elevator travel height exceeds 500 meters, a steel cable becomes so heavy that to go higher, you would normally have to get out at a sky lobby to change elevators, a major inconvenience for a 1 kilometer tall building. Enter Cone Ultra Rope, the holy grail of vertical transportation. Ultra Rope is not a rope in the traditional twisted wire sense. It is a flat, flexible belt. The center consists of 4 high-tech carbon fiber ribbons. Carbon fiber is incredibly strong, but weighs a fraction of steel. The core is encased in a specialized transparent plastic polyurethane coating. This provides the grip needed for the elevator motor to pull the belt without it slipping. While the steel cables weigh 27 tons, the Ultra Rope weighs only 1.1 tons. This is how material science is going to help Jeddah Tower to achieve the highest single elevator lift in the world, a lift of 660 meters. As of 2026, the installation of these systems is a primary focus of the resumed construction. These elevators will travel at over 10 meters per second. You will reach the top in about 52 seconds. It is interesting to note that while the tower has a staggering 252 levels in its total design, the vast majority of the upper structure is a hollow concrete spire. The highest floor designed for public or residential use is level 157, located at approximately 630 meters above the ground. The highest observation deck in the world is situated here. The levels 158 and 159 are technically part of the observatory complex. The remaining 370 plus meters is dedicated to engineering. Levels 161 to 167 are massive MEP floors. They house the water tanks, high voltage electrical equipment, and the massive pumps required to move water to the top of the tower. At level 167, there's a 4-meter thick concrete slab, the sky raft, that acts as the foundation for the concrete spire. The sky raft transfers the loads from the spire's walls down into the main buttressed core of the building. The concrete spire is crucial for achieving the feel that seems to touch the heavens. At the very top, the concrete hollow spire transits to a steel spire. The concrete portion of the spire holds 2 gigantic tuned mass dampers. We will explore this portion later.
Here I have displayed the image of Burj Khalifa and Jeddah Tower. Can you spot a major difference between these two? Yes, Jeddah Tower is much more slender compared to the Burj. To understand slenderness ratio, here is an image of world's slenderest building, 111 West 57th Street, with a slenderness ratio 24:1. The Jeddah Tower's 12:1 ratio puts in the elite club of slender structures. But here is the issue. Slender structures are always prone to the issue of oscillations.
On a windy day, the residents at the topmost floors will be experiencing a nightmare if the sway issue is not addressed. The solution? Tuned mass dampers. Motioneering, the same company behind Taipei 101's famous TBD, suggested a 2-stage damping solution for Jeddah Tower. These TMDs are compound pendulum type and are located within the concrete spire. At level 206, an 870-ton TMD, and at level 218, a TMD of 260 tons will be installed. When the building oscillates, these TMDs oscillate in the opposite direction and activate these viscous dampers. The viscous dampers help to dissipate the energy of the oscillation as heat and helps to kill the oscillation quickly. Now, you might be wondering, why don't the engineers make the building's core extra stiff and prevent it from swaying? No, if the building is too stiff like this, a 190 km/h wind gust at 1,000 meters would cause the concrete to crack. The engineers want a certain flexibility to the towers. The tip of Jeddah Tower is designed to sway between 2.5 and 3 meters. Even at the 500-meter height, the building would experience a sway of 1 meter.
Wow! with the massive Jeddah Tower. Let me enter inside and check out this building. What? Why am I not able to open the door? Let's explore.
The air temperature inside and outside of the Jeddah Tower is shown here. Can you find out a major issue here? You're right. The air inside Jeddah Tower is kept artificially cold, around 22 degrees Celsius, while the outside temperature exceeds 45 degrees Celsius. Remember, Jeddah Tower has 3 massive elevator shafts. Can you tell the effect of such a long column of cold air? The cold air is heavy, and due to the tower's 1 kilometer height, high pressure gets developed at the bottom. This means, from outside, you will struggle to open Jeddah Tower's door. The high-pressure air at the elevator column always wants to get out. High pressure at the bottom of the tower means at the top of the elevator, a negative pressure is automatically created. Here, the outside air wants to get in, always causing a whistling noise. This is a common problem in high-rise buildings known as the reverse stack effect. The main solution to the reverse stack problem is the usage of airtight doors. You will rarely see a standard swinging door at the Jeddah Tower's base. Instead, massive revolving doors and high-tech vestibules ensure that the interior and exterior environments never have a direct open path. Also, please have a look at this force analysis. Even though the pressure is high inside, the geometry of the revolving door makes sure that the user does not have to use much force to open the door. The HVAC system used in Jeddah Tower is not only to cool the building, it's an active HVAC bleed system. The building's computers constantly monitor the pressure at the ground floor. If the push from the cold air becomes too high, the HVAC system can actually suck air away from the lobby area and move it to higher floors to balance the scales. Please have a look at these historical houses of Jeddah, the coral houses of Al-Balad. The high humidity, salty air, and heat of Jeddah even corroded the stones. The visionaries behind Jeddah Tower do not want the same fate for the Jeddah Tower. To overcome the relentless rust trap of the Red Sea coast, the Jeddah Tower utilizes a 3-layered shield of technology. An impressed current cathodic protection system will be in full service to save the piles of this building, which are submerged in salty groundwater from corrosion. Corrosion happens when iron atoms get converted into ions by losing electrons. In cathodic protection, you attach an external DC power source that constantly forces a surplus of electrons directly into the iron. Due to this, steel rebar's polarity shifts in the negative direction. Since there is an abundance of electrons around the steel, it can no longer release free electrons. Thus, the chemical reaction of rust formation is stopped. Standard concrete is actually quite porous. To block salt at the surface, the Jeddah Tower uses a high-performance mix enriched with silica fume. Silica fume particles are 100 times smaller than cement. They fill the tiny pores in the concrete matrix, creating a density so high it is incredibly difficult for salty air or water to penetrate into the rebar. In some sections, the concrete cover is over 75 millimeters, nearly double what you'd find in a normal building. The third and most important shield is Jeddah Tower's structural health monitoring system. If salt levels ever start to rise near the steel, a computer in the building's basement alerts the maintenance team, allowing them to adjust the cathodic protection voltage before a single speck of rust even forms. The skeleton of Jeddah Tower, the high-strength concrete core, is designed to last 200 to 500 years. Since it is so massive and the concrete is so dense, the core essentially becomes artificial stone over time. Elevators, HVAC, and plumbing have a much shorter lifespan, usually 20 to 30 years. With continuous maintenance work, these equipment stay alive. In short, the authorities want the human race's first 1 kilometer tall tower to last for many centuries.
Before you leave, please check out forthepeople.com. Thank you for watching the video. Take care. Bye bye.